So welcome to office hours. Let me know what I can help you with. I've got some windows open with our web assign and also with our special homework. So let me know what you'd like to look at.
We, I wanted to look at some of the questions from test three.
Okay, let's do that. All right. Oh gosh, I haven't posted test three yet. Let me see if I have that in a folder. I do. So are you in the Monday, Wednesday or the Tuesday, Thursday?
Tuesday, Thursday.
All right, so that would be test form A. Can you tell me what number you would like to look at?
Could we look at number two, number five, number six, number seven, and the extra credit question?
Sure. All right, do I have everything listed there that you want to look at?
Yes, and then I also wanted to go over the last special homework. I think was that special homework 11?
Uh-huh.
Okay.
And so special homework 11, and I think
Yes.
that was for Tuesday, Thursday, and I think for that was on subset inclusion.
Yes.
So
Yes.
it was a worksheet for Monday, Wednesday. I'll just write this down so that folks that are looking at the notes can get themselves sorted out.
Hmm?
All right, so shall we start with the test or with the special homework?
The test, please.
And sure. So number two was one of these questions about proving a recurrence relation. So we have a sequence D sub n. And the formula for D sub n is that the term D sub n is 3 times 5 raised to the n for n greater than or equal to 0. And then we want to prove this satisfies the following recurrence relation. And a recurrence relation is generally a relationship between terms and prior terms. And so this recurrence relation says for k greater than or equal to 1, d sub k is going to be 5 times the prior term, d sub k minus 1. Does that make sense?
Yes.
All right. So when we see something like this, one of the things we can do to try to better understand really what's going on is just look at the first few terms of the sequence just to kind of see what kind of sequence is this. And it turns out it's a geometric sequence. So let's just think about this sequence, okay, first, before we try to answer the question, okay? So what is D sub 0? When n is 0, when the indexing number, which is n, is 0, what is D sub 0? According to this formula. See, this formula is what's actually given. This is
Would
what's
it
given.
be three?
Uh-huh. It would just be 3. So let's just take a look at a couple of terms so we can get our heads around what this sequence looks like. What about D sub 1?
15?
Yep, and I'm going to just keep it as 3 times 5 to the 1 because that kind of shows us a little bit more information about the relationship between the term and the formula that defines the term. Does that make sense? Like
Yes.
15, it's true, it is 15. But this is in some sense a little more informative because then when we look at d sub 2, it's 3 times 5 squared. And see, we can start to see a pattern because 3 is actually equal to 3 times 5 to the 0, which you obviously understand because you were able to tell me that the
Mhm.
term is just 3. But but do you see how we can get from D1 to D2 by multiplying D1 times 5?
Yes. And so for this question, we're just finding the sequence.
No,
Oh.
we're going to prove that the sequence defined by this formula is given. We're going to prove what we wish, and what we wish is to prove that there is this relationship. It's called a recurrence relation, exists between a term, d sub k minus 1, and the next term, d sub k. Or you can think of this relationship as being a relationship between a term and the prior term. You can think about it either way. But the point is there's a relationship between consecutive terms. You get from one term to the next by multiplying by 5. And that is the nature of a geometric sequence in general. That means that our common ratio that we're multiplying by over and over again is actually 5. Every geometric sequence, if you go back and look at the notes about sequences, section 5.1 notes, we actually took a deep dive into geometric and arithmetic sequences. And then when we looked at recurrence relationships in section 5.6, was it, or 5.7? I can't remember. It was one or the other. But when we went, we skipped a couple of sections. We did 5.1, 5.2, a little bit of 5.3, and then we skipped to either 5.6 or 5.7. I think it might be 5.6. We talked about recurrence relations. And this is the section that this is in, okay? And when we looked at recurrence relations, we revisited arithmetic and geometric sequences because they can always be shown to satisfy recurrence relations. The recurrence relation that comes into play with a geometric sequence always looks like multiplying a term like d sub k minus 1 times the common ratio to obtain the next term, in this case d sub k. With an arithmetic sequence, the recurrence relation would involve taking a term and adding the common difference to get the next term. See what I mean? So there's
Yes.
always this sort of relationship with those two classes of sequences. It's not always multiplying. It can be adding if the relationship is an additive relationship, as in an arithmetic sequence that has a common difference. So go back and review those notes to help yourself. But what we are asked to do is prove this, okay? So in our proof, we let the sequence d sub n be given by the formula. Or, and I didn't require you to be this formal, but this would be a formal proof. By d sub n is equal to 3 times 5 to the n for n greater than or equal to 0. What do we wish to show? We wish to show that d sub k is 5 times d sub k minus 1 whenever k is big enough. K only needs to be at least as big as 1, because when k is at least as big as 1, then k minus 1 would be 0 at the smallest. And you see this formula only works starting at 0 for the indexing, see? So let k be greater than or equal to 1. The given formula says this. We're just going to apply the given formula. And we did this in class, and there was also a WebAssign problem. Very similar. The given formula says that d sub k is equal to, well, let's just put in a k here, and we can do that because k is bigger than or equal to 1, so it's certainly bigger than or equal to 0. The given formula says d sub k is 3 times 5 raised to the k. That's just by the formula. Do you agree?
Yes.
We, so we'll call this equation star. But because k is at least 1, then the given formula also works for d sub k minus 1. Because if k is at least 1, then k minus 1 is bigger than or equal to 0, right? So the
Mm.
given formula works for k minus 1 as the indexing variable, as n. And we know that that is equal to 3 times 5 to the k minus 1. That's just by the formula that we're given. We're just applying the formula to look at d sub k and to look at d sub k minus 1. Why are we doing that? Because what we wish to show is this particular relationship between d sub k and d sub k minus 1. In order to investigate this relationship, we need to have information about the pieces involved in this equation. This relationship is an equation involving d sub k and involving d sub k minus 1. So the more we know about d sub k and d sub k minus 1, the better a chance we have of establishing that this relationship holds. Does that make sense?
Yes.
The only reason I wanted to go through a few steps of looking at the first few terms is because that's the first step to getting our heads around what this formula even builds, right? And we can see, oh, okay, we're multiplying by 5. Oh, that's all this says, is we're multiplying by 5 to get the next term. See? And here we can kind of see it actually happening. But a real proof requires that we write our argument without using specific values for n or k. We're going to write the argument for general k, okay, and k minus 1. So we want to establish this equation. There are two ways to attack it. There's probably more than two ways, but I can think of two ways. We can start with d sub k and try to work on it until it looks like 5 times d sub k minus 1. Or since it's an equation, then it doesn't really matter which side we start with. We could start with the right-hand side and work on it until it looks like d sub k, the left-hand side. See what I mean? Doesn't
Mhm.
really matter which side we start with. We want to turn one of these sides into the other one. So let's look at two solutions. One of them might be easier. I'm going to start solution 1. I'm just going to start with the left-hand side because I read from left to right. Okay? So here we go. D sub k. I want to turn it into this. Well, what do I have to work with? I have equation star and equation double star. Do you agree that that's what we have? That we know for sure?
Yes.
So we'll substitute in for d sub k using equation star. So we know for sure that this equals 3 times 5 to the k. That's by equation star. That's, we're just using the definition that the formula gives us. All right. Now let's take a look at where we're at. We're at 3 times 5 to the k. We want to get to 5 times d sub k minus 1. All right, we need a 5. We got a bunch of them. We don't know how many, but we've got k of them. K is at least 1. Let's pull out one of them. Isn't this the same as 5 times 3 times 5 to the k minus 1? Just using laws of
Yes.
algebra? Yeah, this is just algebra. Well, what is 3 times 5 to the k minus 1?
It's d sub k minus 1.
Yeah, so this is 5 times d sub k minus 1 by equation double star. It's just, this is the definition of d sub k minus 1 according to the formula. And that's what we wanted. We started with d sub k. We turned it into 5 times d sub k minus 1. Just by using these equations that gave us information about what we know d sub k and d sub k minus 1 actually look like, and a little bit of algebra. How did I know what algebra to do? Well, we started with d sub k. We know it looks like this. And then I looked ahead to see what I needed. I knew I needed a 5. We got numerous 5s here possibly. It might just be one, but that's all we need. Because if there was only one of them, this 5 would be here, and the k minus 1 would be 0, and this 5 to the k minus 1 is really 5 to the 0. Who cares? The point is we can definitely split up 5 to the k as 5 times 5 to the k minus 1, just using, laws of exponents. That's how I knew to take this step of pulling a 5 out. I looked at what I wished. That's why I love writing my wish, because it can really guide me and almost tell me what to do. The other way to approach it, or another way to approach it, would be to start with the right-hand side and turn it into the left-hand side. So if we start with 5 times d sub k minus 1, well, that's equal to 5 times, well, you tell me, what is d sub k minus 1? What do we know?
It's 3 times 5 to the power of k minus 1.
Mm-hmm. And that's by equation double star, isn't it?
Yes.
So we're starting with 5 times d sub k minus 1, and we want to turn it into d sub k, right?
Hmm. So then we just add that 5 back.
Yeah, just to put the 5 to the 1 over there close to the 5 to the k minus 1, and then we realize, oh, that's really going to be 5 to the 1 plus k minus 1, which is 5 to the k. That's just algebra. And what is 3 times 5 to the k?
D sub k.
Exactly, by equation star. So that might even be an easier way for you to attack it. Either way works. It was just a few lines. I gave people partial credit for looking at some of the sequence values. If people, at least, did this and tried to at least understand the sequence, people got, some partial credit for that. But we worked a problem just almost exactly like this in class. And we also had a WebAssign problem that was very similar.
Like,
Would
because
you
I
like
was gonna study after this. I'm gonna look at like the other homework and the web assign.
would you like
Like,
a do later?
yes.
And then we can revisit the do later in another office hour if we need to. So number 2 on test 3, form A, I'll call it 2 prime. Okay. Similar to 2, but it's a do later. Can give you two of them. Let A sub n be defined by the formula A sub n is equal to 2 times 1/2 raised to the n for n greater than or equal to 0. Prove A sub n satisfies this recurrence relation for k greater than or equal to 1. A sub k equals 1/2 times A sub k minus 1. Okay? So it's another geometric situation. I'll give you an arithmetic one too. Let B sub n be defined by the formula B sub n equals 7 plus 4n for n greater than or equal to 0. This is an arithmetic sequence. Prove B sub n satisfies this recurrence relation when k is greater than or equal to 1. B sub k is equal to B sub k minus 1, whole thing plus 7. See, because that's what's happening. Oh, did I say plus 7? That's wrong. The common difference isn't 7. The
It's
common difference is 4. So we'll be adding 4 over and over again to get the terms, not 7. 7 was the initial term. Okay?
Yep.
All right. Now let's look at number 5. Still from test 3, form A. Hang on, I gotta bring my test up here. Form A, yeah. Okay, so, this is a good one. So B sub k is defined to be the interval between minus k and k. And this is for k equals 1, 2, 3, dot, dot, dot. I wouldn't want to start at 0. I wouldn't want k to start at 0 because then this would be from minus 0 to 0, but not including the 0, right? Because soft brackets mean don't include the endpoints. And that wouldn't be a nice thing to do to you. All right, now we're going to address these unions and intersections. And I don't know, and I'm not trying to put you on the spot, okay? I don't know how much of class you might have missed, Sydney. It seems like you're in class most of the time.
I think I just didn't give myself that much time to study, and that kind of messed
Yeah,
me up.
there were some
So,
not, yeah, and WebAssign's not that great for a lot of things, but I will say the WebAssign problems that were similar would have helped you a lot because we had a quiz, but we didn't have a special homework on this, I don't think. So the
mhm.
WebAssign was critical practice. But anyway, drawing a picture is always a good idea with these, right? so that we can just get our heads around what these sets even look like. And remember, these sets are not just sets of integers. They are intervals of the real line. Each one of these has infinitely many real numbers in it. Do you agree?
Yes.
For example, when k is 1, right? What is b sub k? In other words, what is b sub 1?
-1 and 1.
Yep. Well, I'll put the negative in blue. Yeah, it's from -1 to 1. And these soft brackets, do you remember what that means? These soft parentheses? It means we're not including the -1 or the 1. It means open holes. Okay? So b sub 1, we would draw it on the number line like this. From -1 to 1, but we're not including -1. We're not including 1, but all these numbers in between. This is b sub 1. Okay?
Mm.
And what is b sub 2 going to look like?
-2 to 2, and it's not including -2 to 2, so it'll be soft brackets. On the number line, it'll be soft brackets on the -2 2.
Yeah. So I'll do it in red. So from -2 to +2, but not including those endpoints. But it's all the real numbers. Start at -2, but not including the -2, all the way across, including all of the real numbers that happen to be in b sub 1. Do you see that?
Mm.
What about b sub 3?
It would be -3 to 3,
Uh-huh.
not including -3 and not including 3.
That's right. We'll do that one in green. B sub 3 to 3. So we can draw all, I'll do it underneath. See how these are nested? We call these sets nested. And then b sub 4 goes from -4 to 4, but doesn't include the -4 or the 4, but it includes everything in between, right?
Yep.
So you got your head around these sets, right?
Yes.
Can you kind of see the relationship between these sets, how they're nested?
Yes.
So we can make a few notes. Do you agree that b sub 1 is a subset of b sub 2? Everything that's in b sub 1, and we might want to make b sub 1 a little bit darker. You see how it's got everything that's b sub 1 is completely contained in b sub 2, and b sub
Yes.
2 is a subset of b sub 3, and b sub 3 is a subset of b sub 4. These are what we call nested sets because they fit into each other like baskets or nests, matryoshka dolls or whatever, what have you. I love matryoshka dolls. Matryoshka dolls. All right, so when we start thinking about the union, first of all, you have to understand what union means. And then when we start to look at intersections, we have to understand what intersection means. And then we have to just kind of expand our mind to think about an, an infinite union if we just kept unioning forever, or an infinite intersection if we kept intersecting forever. But we can do that. Okay? So I'm just going to kind of do this. First union is the union from K equals 1 to 4 of the B sub K, right? So let's just think
Yes.
about what that really is. It's the open, we call it the open interval from -1 to 1. Open because we're not including the endpoints, open holes. Union, the open interval from -2 to 2. Union, the open interval from -3 to 3. Union, the open interval from -4 to 4. That's what that is. Do you agree? Now we want to figure out what is that set finally. We want to write the answer as succinctly as possible. We want to indicate we understand what that union symbol does. It, so the union is the OR operator. We're looking for elements that are in B1 or in B2 or in B3 or in B4. In other words, it's going to be the set of X in the reals such that X is an element of B1 or X is an element of B2 or, right, X is an element of B3 or X is an element of B4 or any number of those because it's the inclusive OR, not the XOR. We never have used the XOR in this class. So what is that going to be? Let's look at our picture. We want X's anywhere in any of these.
I was writing.
That's,
Can you repeat the question?
well, just tell me what this set is going to be. We'll use interval notation. It's a single interval that can be used to express this union. So your job is to figure out what that interval is that expresses the x's and the reals that are in B1 or B2 or in B3 or in B4.
So is it -1 to
A lot of people put from -1 to 4. I don't understand that. Because here's -1, right? Right?
uh,
But what about all the real numbers that are between -1 and -2? Aren't they in B2?
it's -4 to
Yes, it's well,
okay.
see, because I mean, why would we throw away uh all of these real numbers that are out here up to but not including -4? In fact, if we were throwing them away, why didn't we throw away the real numbers between -1 and 0? Like, why did we stop at -1? Doesn't make sense to me. Can you explain it, what your reasoning was, so I can try to help students not make that mistake in the
I
future? A
I
lot of
think it
people
oh I'm sorry.
Yeah, a lot of people made that mistake, and I don't understand where it's coming from.
I think it was when I was looking at like the when you uh like laid out like all of the unions, I was looking at the beginning and I
Oh, you
saw
were
like the
looking
negative.
here
Yeah, I was
and
looking there
here.
to there.
Thank you. Yeah, but it's not because it's more what's going on here.
To look at the number line and not.
Yeah,
No.
because we could have put these in a different order. I could have said it's -3 to 3, union -2 to 2, union -4 to 4, union -1 to 1. Couldn't I? Does union
Yeah,
care what order these are in?
no. I
No.
think that's what I'll do when I'm practicing, just mix it up so I don't make that mistake on like on the final.
Uh-huh. And I would suggest you try to get a picture in your head of what these sets actually look like so that you can just see, oh, anything that's in any of these, well, it starts back here and it goes all the way to here.
Okay. Yeah, now I get it.
Thank you for explaining that to me because I couldn't figure out for the life of me how that was happening. Also, I thought maybe some people just didn't know what it was and they thought they might get half credit if they got it half right. Like they weren't sure if it was one or four. So, like, they would put one in one spot and the other in the other spot, and then they would mix it the other way, hoping for half credit. I'm not even kidding, which is a strategy. That's not a very good strategy, but it is a strategy. Now, what about the intersection from k equals 1 to 4 of the b sub k? The intersection operator is our AND operator. We want reals that are in all of these. So it's going to be the x's in the reals such that x is in B1 and x is in B2 and x is in B3 and x has to be in B4. It has to be in any x in our solution has to be in all of these.
Would it
Mhm.
be -4 to 4 again?
Okay, let me ask you this. Let's take a look at that. So you're thinking anything that from -4 to 4 is going to be in all four of these sets. All right, so let's look, for example, at -3.
No, it's not
Is
in there.
-3 in B1? Nope. Is
No.
-3 in B2? Nope. It's not even in B3. It is in B4, but it's not in B3 or B2. It's got to be in all four of these. That's what this means. So which X's are in all of these?
-1 to 1. No.
Because these are
No.
nested sets. It's that middle one. It's that set from -1 to 1. Or you could just call it B1. Either one is fine. Now we're going to bend our minds a little bit. We're going to think about this picture, but we're going to think about taking a union that goes on forever, where K just gets bigger and bigger and bigger. We're not going to restrict ourselves to just B4, because remember the union of just the first four of them was the B4, right? Because it was the biggest one. And we're taking any element that was in B4 or B3 or B2 or B1, right? But if we go on forever, we're saying just keep playing this game. Just imagine you just keep drawing them like B5, Union B5, Union B6, Union B7. Keep on going forever and ever. What real numbers would be in this or this or this one or the next one or the next one or B100 or B1 million? Because the X's in the union or the X's that are in any one of those don't have to be in all of them, could just be in, well, as a matter of fact, any X that is in one of them is in an infinite number of them, but that might not help you that much as just thinking about keep drawing these forever. What do we get when we union up all those sets?
negative infinity to infinity.
Exactly. And then finally, the infinite intersection. Well, it's helpful to understand what sort of restrictions came into play with this little finite intersection. Just this little finite intersection, we were looking for x's that were in all of these, but the only x's that were in all four of these were only the ones that were right in the middle, right?
Mhm.
Well, does it matter if you keep including more and more sets in your intersection when they're nested like this?
Then the negative 1 to 1 is still going to be in the middle.
That's right. These are the only x's that will be in all of these. That's exactly right. The specific nature of this picture is part of what defined these unions and intersections. The relationship between these sets, the fact that they were nested, mattered. And the way that they were nested. The first one was the smallest. It was inside the second one, which was inside the third one. That doesn't have to be the case. It can, the pictures can look different depending upon how we define the set, B sub k or A sub j, or however we decide to call it, however we decide to assign variables to the. So let me give you some do laters for this, shall I? Try to give you a couple of different kinds. Find the same unions and intersections as in problem 2. Uh, problem 5. Okay? So from one to 4 should do it. That should give you enough of an idea if you draw the picture. And then from 1 to infinity, okay? I just want to write several problems down. First one is going to be that B sub k is equal to minus 1 over k, comma, to 1 over k. These will be nested, but in a different kind of way. All right?
Mhm.
5 double prime. B sub k is going to equal k minus 1, comma, to k, square bracket. I'll do one more.
Okay. Yep.
So if you think carefully about them, by the time you're done with those, you're going to be an old pro at
I
interval
hope.
notation and indexed unions and intersections. It's kind of I like these problems because they measure your mastery of a couple of different concepts, unions and intersections, as well as indexed sets. You can see why, this is a problem that I like. I like you to demonstrate that you've understood things. All right, so is that okay? Is that good? Shall we move on to number
Yes.
6? All right,
Yes.
number 6. You go back and look at the class notes, and I hate to keep harping like that, but we did couple of these in class, and there was at least one, maybe two, I think maybe two in WebAssign.
I don't know what happened to me with this one because on the WebAssign
You
and
did
when I was
fine.
practicing with like practice problems that I had, I was doing fine. And then I think I just had like test anxiety and everything just went poof.
Oh man, I hate that. Let's simplify n plus 1 over n minus 2 for, and didn't I say assume n is a reasonable, you know,
Yes, you said assume n is any integer where n is greater than or equal to 2.
and that key phrase there, any integer, where this is defined. The smallest for which this could be defined is 2 because n minus 2 is 0, and these aren't defined. These n choose r is not defined unless both of the quantities are at least 0. It's negative numbers don't help us. All right, so let's just recall, and the formula. I'll do it with other letters. S choose R. It's a number of subsets of size R that we can find given a set of size S. So it's defined to be S factorial divided by R factorial times S minus R quantity factorial. Okay. And there was a worksheet problem like this or a homework problem, depending upon which section you were in. All right.
Yep.
So n plus 1, choose n minus 2, by definition is, okay, n plus 1 is our S, right? So it's n plus 1 factorial on top. We actually have to be a little careful on the bottom. R is n minus 2, right? So R factorial would be n minus 2 quantity factorial. Then we need S minus R. All right, so we got to be careful. S is n plus 1 minus R, which is n minus 2. That whole thing, quantity factorial. Does that make sense?
Yes.
All right, so before we start attacking, simplifying all this stuff, I want to just figure out what this is. So it's n plus 1 factorial on top. We'll deal with that in a minute. On the bottom, we've got n minus 2 factorial. And let's just see what happens when we distribute this minus across n minus 2. All right, so we have n plus 1, just copying those down, minus n. And what is minus a negative 2?
Plus 2.
Plus 2. So we've got n plus 1 factorial on top. On the bottom, we've got n minus 2 factorial. And this is n minus n. The n's go away. But 1 plus 2 is still there, and that's a grand total of 3. All right? So just
Yes.
getting this s minus r factorial correct was a little bit of a chore. Now we want to simplify it. And it's helpful to look at a number line and just realize, okay, here's n plus 1. The integer right before n plus 1 is what?
N plus,
No,
oh
right
no, n.
before. Yeah, n. And what's right before that?
N minus 1.
Good. And what's right before that?
N minus 2.
All right. That would n plus 1 is bigger than n minus 2. Do you agree?
Yes.
So we're going to expand it because n plus 1 factorial is, by definition, n plus 1 times n times, keep going down, n minus 1 times, we can stop at n minus 2 and factorialize it because that's what by definition this is. This is, if n was 10, this would be like 11 times 10 times 9 times 8 factorial. Right? So we can
Yeah,
stop. And why did we stop with the n minus 2 factorial, do you think?
because we have one at the bottom which can cancel it out.
That's exactly right. So these two go away, and we're simply left with n plus 1 times n. Don't have to use parentheses around the n, but I'm doing it. N minus 1, whole thing, and of course 3 factorial is 6. Right? Because 3 factorial
Yes.
is 3 times 2 times 1 times 0 factorial, but 0 factorial is 1. But that's technically what it is. It actually goes all the way down to 0 factorial, but 0 factorial is 1. And the reason it's defined to be 1 is otherwise all these would turn out to be products that are 0, and we don't want them. Okay,
Yep.
you want a couple of do laters?
Yes.
Go back and look through all the class notes and do all those do laters. That would be good practice. Like, how many students actually did all the do laters before the next class? I tried to at least give you one or two every single class. And there was a reason I did that. It's not just because I like green stars.
Use them for for studying for the tests, and some of them I would try, and then if I didn't know, I would wait to see if it was on like the warm-up problem before we started the new subject.
Or you could have come to office hours and said,
Yeah,
hey,
I did have time. That was the only thing.
isn't it awful? N plus 2, choose. Well, let's keep it simple at first. N plus 2, choose N. Okay. It can be A. B can be N plus 3, choose N minus 1. And C can be N plus 3, choose. Oh, did I put N minus 1 there? I'm going to put N plus 1 there. And then I'll put N plus 3, choose N. Okay, that'll give you some practice. And just assume N is big enough. Okay? If we assume N is at least 3 for all of these, then it'll work. That's more than we need for this one. Here we only need N greater than or equal to 2, and it would work out. But we'll just say N greater than or equal to 3. And anybody that has a beef with it, good for them. It means they understand what's really required. All right. Is that okay? Did you
Yep.
get a chance to write those down here? Put them back up.
Yes,
All right. So
I
the
did.
next number 7.
Mhm.
Okay. So C equals, and for the definition, you have to make a choice about where to start the indexing. So I just decided to start the indexing at 1, even though we applied it starting with 0. But anyway, a collection C equals the set containing A1, A2, up to A sub n of subsets of A is a partition of A. Partition. Did I say partition? Overkill. Partition of A if And just remember, each of these A sub I is a subset of A, okay? There's three properties. Each of these A sub I's needs to be non-empty. They have to be pairwise disjoint sets. That means if you take any two of them, like A sub I and A sub J, and you look at their intersection, that intersection needs to be empty. None of these should have any elements in common. Whenever I is not the same indexing, it just means make sure you take two different ones. Saying whenever I is not equal to J is the same thing as saying make sure you're intersecting two different sets. You don't want to try to intersect AI with itself because that won't be empty because AI is not empty. And of course, AI intersect itself would be AI. And the third thing is that if we take the union of all these, however they're indexed here, I'm starting at 1 and ending at n, but however they're indexed, if you take the union of all of these, that should give you A. A is the union of all. So it splits A up into subsets that are disjoint from each other, but the union of all of them is A. Does that make sense?
Yes.
All right, so you were given that A, our big set that we're going to try to partition up, is the closed interval from 0 to 10. So you have to understand that this is not just the integers from 0 to 10. It's all the real numbers from 0 to 10. So I said, notice A is an interval of the real line written using standard interval notation. Just to remind you, this is not a finite little set with 11 integers in it. It's a real interval. And then we define A sub k as the interval that starts at k and ends at k plus 1. And then the collection started with A sub 0 and went up to A sub 9. You had to look at the indexing numbers to understand. And then we're going to verify each property of a partition or explain why this collection does not have the property. Okay. So property number 1. So we're looking at, each of these, A0 up to A9, right? In fact, it might be helpful to realize A0 would be the closed interval from 0 to 1, wouldn't it?
Yes.
And A1 would be what?
The closed interval from 1 to 2.
Great. All the way up to A sub 9, what is it?
9 to 10.
Great. So can you see these in your mind?
Yes.
Like you could draw a picture of the number line. So here's A1. No, A0, sorry. And then here's A1. And then there's A2 that goes from 2 to 3 and includes the endpoints all the way up to A9, right? And it includes 9 and includes 10. These include the endpoints, right?
Yes.
So it's a very different kind of set than those sets we looked at a few minutes ago with our B sub k's, isn't it?
Mm-hmm.
Because they're not nested, that's for sure.
And they also include the endpoint.
And they do include the endpoints, and that's going to matter here in a minute. So let's look at why A sub k is not equal to the empty set. Now notice I'm making you practice here. I called these A sub k. The definition is in terms of I, but you should be comfortable with realizing it doesn't really matter what letter we use, does it? It's just an indexing variable. The definition for a finite partition is starts with indexing equal 1. Ours started with indexing equal 0, but it doesn't matter. You could rename these, you
Mm.
know? Okay. So let's look at these. Here's A0. Ooh, it includes the endpoints. Here's A1. It includes the endpoints. AK includes the endpoints. So what's an easy way to verify that A sub k is not empty? Like what is an element for sure that is in A sub k?
0, 1.
Only if k is 0. We want to argue this all in one fell swoop because we don't want to write 10 different statements.
So just k to k plus 1?
Yeah, notice, isn't k an element of A sub k?
Yes.
It's right, it's the endpoint, it's in there. So A sub k is not empty. That's all we need is one element. It's true, there's an infinite number of elements between 0 and 1, including 0 and 1, but for sure, the first, the left endpoint is in there. And that way we can sort of talk about them all in one fell swoop. Does that make sense?
Yes.
So property one is done. They're definitely all non-empty sets. Now let's think about property two. So drawing this little picture helped. Realizing that the endpoints are included is certainly going to be critical here. If we take any two of these, AI and AJ, and intersect them, look at their intersection, is that always guaranteed to be empty?
No.
Good. So give me a counter example. Just pick your favorite A sub I and A sub j that are between 0 and 9. A sub 0 through, and tell me, pick two where you know that their intersection will not be empty.
Um, 1 to 2 and 2 to 3.
Okay, so A sub 1, which is square bracket 1 to 2, A sub 2 starts square bracket 2 and goes to 3. And if we intersect those, right, what do we actually see that they have in common?
2.
Yeah, they have one single little element, but that's enough to make that intersection not empty. So yes, property one was good, but nope, property two failed. See it?
Yes.
This was a hard test. I think it was this was a tough little question. It was, and because we'd practiced so much with union and interval notation, I made that worth more. I only made this worth 12 points. This was sort of my separator problem.
I think for me, again, I just needed to give myself more time to study because going over this, like right now, this doesn't seem that hard. A lot of this stuff doesn't seem that hard to me. I think I
Good.
just needed to do some more practice problems, which is what I'm gonna do today because that's what I've been doing like all week. I've been doing like at least 30 practice problems from each test, not like together, but this week I focused on test one, and then this weekend I'm gonna do test three, and then test two, and then I'm gonna do it all together 2 days before, and then
That's a
I'm gonna be
really good
ready.
plan. That is an excellent plan. And you can go into the ebook and look at the end of each section and find problems, right?
I have been doing that and using those as well, and then like finding some online and then like looking at the answer after, and then if not, I haven't
Right.
I don't look at any YouTube videos. I mostly look at the notes and the notes that you posted because sometimes people do it differently and then I'll get confused. But I try my best to like
But if you want
use
to
my
look at
notes.
videos, watch the office hour videos.
Yeah, I will. I actually will. I will.
The office hour videos are great. We went over a lot of solutions to different stuff over the semester. And, it's me giving the office hour, so you're not going to be confused. Let's take a look at that last property. The last property says if we take the union of all of these elements, these subsets in this collection, we should get A back. So let's take a look. Starts at 0 and goes all the way to 10, right?
Mhm.
We want to take the union of these. So we're looking at the union from I equals 0 to 9 of the A. Well, I should say K because I used K, right, for the indexing variable. I should make that a K. But the point is, we're looking at unioning all of these up. So we're looking at A0, union A1, union A, and just keep on going up to A sub 9, right? And it's
Yes.
good that we looked at these and looked at pictures, right? So we're
Mhm.
looking at from 0 to 1, union from 1 to 2, union, keep on going to the very last one from 9 to 10, including the endpoints. So if we union these up, and union is our big fat OR operator, do we get everything from 0 to 10, including the end?
Yes.
Yes, this definitely is a yes. So that was part A, was check the three properties. And once you've done that, then part B was simply, do you know the definition of a partition? Because the definition of a partition simply says it's got to have all three properties. And if you didn't remember that, I gave you the definition, right? So
So
is
it's
this
not
yeah, yeah. C is not. Why not?
um because for property two, AI union AJ is not empty.
Yep. Property two failed. No, these are not pairwise disjoint. Just to give you a little lingo, remember pairwise disjoint? That was what that meant. They're not pairwise disjoint. All right, so if you're looking for do later on this, we can go back here. Here I'm going to say, does the collection that starts at B1 has B2 and B3 and B4, because that's what you're going to actually be looking at closely when you draw your pictures. Does it partition -1 to 1, which is going to be our A, all right?
Mhm.
All right, and then for the second one, does the collection, which is going to be the same sets, because you're looking closely for those first four. I figure if you see the first four, you understand what's going on. Does it, oh, partition. Well, I guess the TI, should have reserved it for that. Does it partition A equals from 0 to 4? And then here, does C equal B1, B2, B3, B4, partition A equals 1 to 6. Okay,
Yep.
so that'll give you some extra practice. And you may even, okay.
It's the
And
extra.
more than just partition, check each three of the three properties, like practice checking all three properties, okay?
Mhm.
I mean, to get the most out of it. All right, so that was all from the test except for the extra credit problem.
Yes.
What was that extra credit problem on test 3 Form A?
Let the universe be 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Find one collection of subsets of the universe that satisfy all properties listed below and define only one set, which is either set A, set B, or set C. So all properties are satisfied for that single collection. And then verify each property to maximize points. Oh, well, that was the instruction. Um, and then it was like, um, I is A is a proper subset of B, A and 2 is A, or double I is A and C are disjoint, and the third one is A cross C has 12 elements.
3A cross C has 12 elements. All right, so you got to know what a proper subset is, you got to know what disjoint means, and you have to know what A cross C looks like. So A is a proper subset of B. So whatever A and B we build, A has to be a proper subset of B. Tell me what I need to do just with words, or you can give me an example of an A that's a proper subset of B, and we can tweak it later if we need to make it bigger or smaller. What does proper subset of even mean? All right, so there's problem number one. Do you know what subset of means?
Subset of, isn't it all of the elements in the subset are in, well, are in the,
Yeah, it's called the superset. All the elements in the subset are in the bigger set, the superset. Yeah. So all the elements of A have to be in B, right?
hmm,
But proper means B's got more than A does. B's got something in it that A doesn't have. That's what proper means. So not
okay.
only is A a subset of B, B is strictly bigger. It's sort of like the difference between less than or equal to and strict less than.
I understand because less than or equal to also includes the value that they're being less, that is supposed to be less than, right? And then if it's just less than it,
It can't be the
it's,
same. They can't be
yeah.
equal. Yeah, because A is a subset of A, but A can't be a proper subset of A. It's a subset of A. You know, a set A is always a subset of itself, but it can't be a proper subset of itself because it can't have something it doesn't have. So that forced A and B to actually be two different sets. And that was the only requirement that forced A and B to be two different sets. The fact that A and C are disjoint forced A and C to be two different sets. Does that make sense?
Yes.
And it also forced B and C to be not the same set. One and two together forced all of these three sets to be different. It didn't mean they're all disjoint. B and C can share some elements as long as A and C don't. It's okay for the extra elements of B to also be in C. That's not a problem. But A and C can't share any elements because they're disjoint. And then give me some choices of how big A could be and how big C could be to make sure A cross C has 12 elements. There's numerous ways to do that.
Um,
So we have to understand that A cross C is a set of ordered pairs. Like with binary relations, the elements are ordered pairs, aren't they?
yes. So could A be like size 6 and C be of size 2?
Yeah, that'll work.
And then A could also be of size 4 and C
Yep,
could be in size 3. Oh,
yep, yep. So it might almost be easier to just figure out how big you want A to be and then work from there. Now that you've like reading through all these kind of that gives you kind of a handle on where to start. Like, okay, A is going to have a certain size, right?
mhm.
So pick your poison. What size do you want A to be?
Let's say 4.
All right, so A is going to have four elements. You tell me what you want to put into A.
Um, just like 1, 2, 3, and 4.
And that's what I would do. Keep it simple. Great. Now, two other things have to happen. We got to build B so that A is a proper subset of B. Then we got to build a C that doesn't touch A at all. C and A have to be disjoint. But B and A are going to overlap because A's got to be a subset of B, but it's got to be proper. So what do you want to make B? It's got to have A in it, right? So what's going to for sure be in B?
1, 2, 3, and 4.
Yep. And
And
now
then
that makes A a subset of B,
mhm,
but we need it to be a proper subset of B. So what else do you want to put into B?
5, 6, and 7.
Why not? We can always erase if it turns out there's a problem. But
Okay.
so far, A is definitely a proper subset of B. Now we got to figure out C. A and C have to be disjoint, but A cross C has to have 12 elements. Now, you already decided how big A is, so how big is C going to need to be?
C needs to be 3 elements.
Okay, so build me a three-element C that satisfies that A and C are disjoint.
7, 8, and 9.
Why not? It's that simple. And so how do we verify it? One, A is a subset of B because all elements in A are in B, but B also has 5, 6, and 7, which are not in A. This makes A a proper subset of B. And in fact, there's a notation that goes with that. You know how it looks? A is a subset of, but not equal to B. That's actually one way to denote it, right? We're not putting the slash through the subset. We're only putting the slash through the equality possibility. So that's one, that's one way that some people denote proper subset. Other people denote it like this, A and just the little soft less than or equal to. I mean the little soft less than, but not the equal to. Both of these notations can be used for proper subset. But you see, advanced set theorists use this notation for subset of. So like set theorists have different kind of notations. They have to tell you what they're doing. You have to be familiar with their work. So let's verify. All right, what about two? How are you going to tell me how to write that A and C are disjoint? What would you do to try to verify that?
A and C are disjoint because they don't have the same elements.
Not that they don't have the same elements. A and B don't have the same elements, but they're not disjoint. Stronger than don't have the same elements. So see, they have some of the same.
Because none of the elements in
Yeah.
C are in A.
Yes, because none of the elements in C are in A. And you know what our notation says? A intersect C is equal to what?
So
That's right. That's the definition of disjoint. So you could just say that. Notation's so handy. How would you verify property three?
Can I just like put A cross C?
Yeah, A cross C has how many elements? Four.
It has 4 times 3 elements, which equals 12.
That would be fine.
Okay, got
Another
it now.
another fact is that the size of A cross C, this is actually, this absolute value around A cross C means the size of A cross C. It's actually equal to the size of A times the size of C. Or you could put a little cross there. It's a little confusing. Sometimes people use this notation, the size n of A cross C. This isn't, let me just say these are notation. These are different little notation things. Some people use absolute values to denote the size of. Some people say n of, it's n of A times n of C. Just multiply the sizes together. Okay, just a little notational stuff for you there for future reference. Okay,
Yep.
this is absolutely fine the way you did it. But notation gives us a way to agree and write things succinctly. Notation is so handy. Now, I know that you also would like to look at worksheet 11 on subset inclusion. You know what I'm going to ask you to do since we've been at this for about 100 minutes,
Mhm.
125 minutes? I'm going to ask you to join me later in the weekend for round two. And
Okay.
then round three and round four all week long. We can go
Yes, I
through.
will definitely be there.
Sydney, it's such a pleasure always to see you in class. Uh,
Of course, I enjoyed this class so much. This is my favorite class this semester.
I'm so glad to hear that. Uh,
Mhm.
I really love it, and it's so much fun. So I only regret that we have not had more time together in office hours because this is where it really, I think this is where it happens. I think
Yeah.
this is where we can really spend the time. So just if you write anything on social media or hate my professor or whatever, just please point people to the office hours. Just say, hey man,
Did
go,
I did write a rate my professor little thing, and I did say like I really did like this class, but if you guys are like if anyone is struggling, she is open for office hours and just like she gives the time to help you. And I've read like the bad reviews because I didn't even look at your rate my professor, but after like the first 2 weeks, I was like, okay, I think I like this class, and then I did put a good review because
I
I
appreciate
genuinely
it.
do like
Yeah.
this class.
Yeah. I think I read my rate my professor one time and I like cried for days. I'm not even kidding. I like cried
What?
for days. And this was a while ago. I was a younger, I wasn't as secure, I wasn't as good, you know, but I threatened to sue them unless they took some of them down that were like just blatantly false. Like, one person said, everybody failed it. And I said, that's blatantly false, that's definitely not true. Take it down or I'm going to sue you. They took down like four, I think out of the seven, they took down four. But it's like I decided I'm never going there again. But, people do look at that, right? Students do
Yeah.
actually look. So all I want is just a little help to get you young people that do go there to say, hey, do it, but just take advantage of the help because this is not an easy class. But you know what? When you take the time, I think you just nailed it. You were like, I didn't spend the time.
Yeah,
It's right.
and I'm being honest with myself. Like it wasn't even the teaching because you're a very organized teacher,
I
and
am.
all of the
That is
notes are
true.
very laid out. It was just I didn't take the time to really like
Go
study more.
back,
Yeah, and
like
that was
right,
on me.
like it's not a class where you can just, you know, even the homework helps. The special homework helps because it makes you take the time.
Mm,
But I know that sometimes there are shortcuts there too. We don't need to go into it. And then you didn't really understand, right?
yeah.
You're right. Remember that first homework where you had to write down. how many hours a week you go to work and how many hours a week you commute and how many classes are you taking and multiply credits by 3 to get study hours and add all that up. And do you really have enough time in your
Yeah.
week, right? Like I did that for a reason. And I'm telling you, the people that were over scheduled on homework one, that is such a good predictor of not passing this class. It's like I'm gonna do an experiment sometime where I photocopy all those homework ones and then hold on to them and then do a statistical analysis because I really do think time is the key. You're right. It's about time.
Yep. You have to be consistent because every day since I got back from break, especially with test one, I looked at it and
Uh-huh.
I've been just doing practice problems of every single section. And I've like, I think yesterday from test two, I did 50 practice problems, but I didn't think it was a hassle because I was having fun. I really love math. So I was having fun with like doing the problems and I had like a little show on and I was just writing and going and going and going.
I'm
And I
so
could do that.
glad. I'm
I
so
could do that
glad
for
that you
hours.
I'm so glad to hear you say you love math because you know what? That is such a great uh love to have. So you might consider taking a math minor. Are you a computer science major, right?
Yes, my parents have told me to take a math minor. I don't know. I think I wish I was like I could just get it like right when I learn it, but I know that's not me. I know I have to study and I don't mind
Me
studying.
too. Me too. I don't just
Yeah.
get, man, I went to grad school with these people. They'd go to movie nights and I'd be like, nope, I'm going to sit here and work on it till I
Yep.
understand it. It took me like twice as long as everybody else, but but perspiration, it will get you the A. It will get you the understanding, you know.
And I always believe that the amount of work that you put into something and the result is that you get back is literally what you deserve. So, and I wasn't even like I was upset with myself when I saw my test grade, but I wasn't like, "Oh, this is wrong." Like I knew that for me, like this is what I deserve. Like I didn't put the time in, but I know like I didn't like sit and be upset. I was like, "Okay, now I got to study because I got a final. It's not over. I
No,
can
it's
do
not.
this."
It's not. And I really respect everybody that just keeps showing up and then learn because part of learning is learning about yourself and learning about what's required. That's a real mark of maturity when you can say, "Hey, this is my responsibility. This is on
Yep.
me." That means you have grown in lots of different ways during your time so far at Towson. It means you're learning life lessons as well as mathematics lessons, and that's a great thing. It's going to serve you so well. Just take responsibility, and you'll be a happier person too.
Yep.
'Cause
Because you learn from your mistakes and don't blame it on anybody else either. 'Cause
exactly. And
it's on
believe
you.
me, and doesn't matter how old we get, there's always room for growth. We don't maybe make the same mistakes or we make them much less frequently and
Yep.
but man, if you're a thoughtful person, you do look inside and ask, what was my part and how can I get things to be even better? And then things do get better. And it
Yep.
really things get better. So good for you. Thank you so much. Because of you, we have a really nice video with lots of nice solutions. And I hope you have a wonderful weekend. We can do this again tomorrow or Sunday. Well, we'll have one Sunday, but you just let me know. And
I'll probably email you about doing one tomorrow. I don't think I can make Sunday because I have work. Wait, actually, I think I can make Sunday. I don't think I work.
well,
Wait, I think I
I'm
can make
perfectly
Sunday.
happy to move into something else tomorrow and then something. And I'm going to put some notes in. You know how the description can tell you what's covered? I'm going to put in
Hmm.
the description what's being covered so people can know without looking at the whole video. I try to do that. I don't always do it, but I try to. All right. As you go, hey, as you watch those videos, if there isn't a description, if you want to email me a description, just a list of the topics or that are covered, I can give you extra credit because then I can just cut and paste from email into the description boxes and it'll help everybody.
I'll definitely do that.
Thanks. I
Of
need the
course.
help.
Thank you, Professor. I really appreciate you taking the time to help me.
It's my pleasure. See you tomorrow. You'd let me know
All
what
right.
time.
Yep, see you tomorrow.
Not too early in the morning. Good night.